just remembered I forgot to send the video out from yesterday as I was walking in. I don't know if you guys have went into my math or my stat lab this morning, but it has a new look. So not to be alarmed, they always do their updates during the summer so that they don't affect the regular school year as much. See, it looks a little different over here on the left-hand side. The dashboard looks the same, but over here it just looks a little different. It has all the exact same stuff. What I don't like about it is I can't close down the window, or I haven't figured out how to yet. So due tonight by midnight is 8-1. And then 8, 2, and 3. The stuff we're going to do for the rest of this chapter really piggybacks off of 8-3. So 8-3 is really the most important section from this chapter because it puts together all of our ideas for hypothesis testing. All right? Anybody have any questions about the homework?
On number 3.
For which one?
8, 2, and 3.
Okay. Oh, okay. Well, it's not due till tonight. Bless you. And really the stuff that we're going to cover today for 8-4 comes directly from the stuff for 8-3. So as long as you can identify the Z statistic, then it's pretty easy to do the section 8-4. All right? Number 3, you said, Crystal?
Oh, you know what, on this one, I got that part right, and then when you move on to the second answer, I was completely lost.
So that one's definitely that, right? Because that's the only two-tailed graph, right?
And less than.
Less than the negative and then greater than the positive. So this is the same as the absolute value, right? It could have been expressed that way. So this or statement could have been the absolute value of Z is greater than 1.28, right? It represents the same information. So then you check it. Now it wants to know, bless you, it wants to know the probability of type 1 error, which is what? Which is?
Your A.
Alpha, right? Your alpha. So all it is the area under the curve that's been highlighted. So what we need to do, no, go ahead, do you have a question?
No, I'm listening. Go ahead.
So what we need to do is go look at our Z chart, determine what the area is in one of the tails, and then double it.
So would you look for 1.28?
In the Z chart, but you'd have to do 0.5 minus, right? Because the chart just gives us, the interior area, not the exterior area.
Okay, so you would find 1.28 and
on the chart, and then do 0.5 minus whatever that value is. All right, so let me go pull up the textbook. And of course that's going to kill the... I don't think it's going to let me while this is open. There we go. So let's go. So all I'm doing here is looking for the Z chart. The internet's been going slow. It was slow in my office too. So the Z-chart, I believe, is on page 773, right? Okay, so there's our Z-chart. Now what we want is the area in the two tails, right? So the graph that was just up had this, right? So here's our normal curve. Here's 0. I have the value of 1.28 with it shaded over here, and the value of negative 1.28 with it shaded over here. And of course, this is the z-axis. Now what the chart tells us is this area, right? Mm-hmm. So what I need to do is 0.5 minus whatever the area is in here, right? Because half of it is 0.5, so then we go into 1.28 right there, 0.3997. 0.3997, which is what exactly?
0.1003.
But that's just one of the areas. So what do I need to do to find out this area? Of course, this thing is symmetric, which makes it nice. So what's the area in here? Multiplied by 2. So in both places, it's 0.1003. So I need to add the two areas together, and I get the answer is alpha equals 0.2006. I think it said round to 3 decimal places in the homework. Right? So it'll be 0.201. So let's go back and look. Man, I wish I could pull that. Maybe it'll let me do it. Because it even tells you what alpha is defined as, right? So the values have changed, but notice how it calls this alpha, right? The rejection region is alpha. Is equal to alpha is the rejection region. So let's do this one. So part A says Z is greater than 2.575. Is that the upper tail, the lower tail, or the two tail?
The
Upper tail. All right, so that's going to be this one. So we hit part A. Final check. Okay, it's correct. Now it wants the value of alpha. So for alpha, what I'm going to do is 0.5 minus. Oh, look at that. I forgot to erase it. We have our normal curve. And then we came up with 2.575. So we want this area here. So it's going to be 0.5 minus. So alpha is going to equal 0.5 minus whatever the area is. Right, whatever this area is at 2.575. Which in the back of the book, you don't exactly have 2.575, right? You have 2.57, and then 2.575 will be in between 2.57 and 2.58, which is 0.4950. So this would be minus 0.4950. So that implies that alpha equals 0.005. Which makes sense because that was our 99% confidence interval, right? This was the Z value that went with the confidence interval, so that would mean that half of 1% was on this side and half of 1% would be on the other side. Right. Now this is just setting up our rejection region, right? So this is step 4 from your list of steps, right? Because step 1 was the null hypothesis, which that's a good thing to just write down again to jog our memories. So 1 was the, let me make a little more room. 1 was H naught, 2 was HA. What was 3 in the order?
It's correct test.
Pick the correct test statistic. Up to this point, the only one we've dealt with is the Z statistic. Today we'll see the T statistic, all right? So it would be the pick test statistic. Number 4 was what?
The reject region.
Right, find rejection region, which is alpha. I.e., which means, for example, alpha, right? What was 5? Assumptions, right? Which, with these, since we're using the Z statistic, we can go ahead and say that it's going to be approximately normal. We can use the central limit theorem. What was 6? Calculate test statistic. And then what was 7? Conclusions. And the conclusions can only be one of 2 things. A is reject H naught, and this thing is just about to go. I forgot to get a marker again. And then this B is fail. Fail to reject H naught.
When you're going through those and
Yes.
you're reading them, and maybe it's just me, but does it seem like the reject is opposite? Like when you get your number, it almost seems like, to me, how do I explain it? It's greater than 1.96. I was using the number that they were giving.
Right, so if we calculate our test statistic at number 6 and it falls in this region, then we reject H naught. That's why we call it a rejection region. Does that make sense? What's going on?
So it almost is opposite if you don't really understand step 4, that alpha is the rejection region.
Right, alpha is where it gets rejected. If we find that 6 falls in the area that is alpha, then we reject. That's why we don't call it the fail to reject region. That's why we call it the rejection region.
So the highlighted...
Right, the tails is the rejection region. And see how right here it's saying reject H naught? If our Z statistic falls within that area, and we reject H naught. Right? If it doesn't fall in there, we have insufficient evidence to reject H naught. We do not accept H naught, right? Because we don't know what beta is, what the chance for type 2 error is. We do know what alpha is because we set it right here at the very beginning of the test. It's something that's set by the researcher. And really, if I wanted to conduct a good test, I would make alpha very small, right? I would make the probability of type 1 error as small as possible. So you want to make alpha really, really small in a perfect world, right? The smaller, the better. The more confidence you have, all right? And what's nice about what we're doing today is it piggybacks right off this stuff, okay? What we're going to do is called the p-test. What the p-test is once we calculate this test statistic, if it falls in the rejection region, the p-test will just be the area to the right of whatever this test statistic is, which is not going to be the same as the rejection region. Right? It could be. So say if we had a problem here, you know, and I found that my Z was equal to positive 3, all right, if I did the whole problem. Positive 3 would definitely fall in the rejection region, right? Do you guys agree with that? Because it's right of 2.575. What the p-value would be is just the area to the right of 3.
Is it 0.5 minus that?
Well, it would be 0.5 minus what it is at 3, which would be 0.499, which is like 0.001 would be the answer for that. And, you know, we'll see examples of that today. But let me go ahead and put the correct answer right here. What did we come up with? 0.005 for alpha? And there we go. So that's alpha, right? That is our area of our rejection region. Basically, the way to think about that is the chances that we're going to reject H naught is 1/2 of 1%. So if we do end up rejecting H naught, then we're pretty sure that the null hypothesis was incorrect, because our probability to reject it was very, very small. Right? It was only 1/2 of 1%. So if it does fall in that rejection region, we're pretty certain that the null hypothesis is not true. So that's why we like to make alpha a really small area, as small as possible. Right? Let's look at number 3. I had a question about that one. A random sample of 100 observations from a population with standard deviation 63 yielded a sample mean of 111. Complete parts A through C. Test the null hypothesis that mu equals 100 against the alternative hypothesis that mu is greater than 100. Is this going to be a one-tail or a two-tail test? One tail, and it's going to be the upper tail. Right, exactly. Good stuff. There's a couple more. Here we go. See if this one works. Nope. All right, so let's go ahead and do this problem. So let's start over here. So what I'm going to do is take my general definitions and I'm just going to fit them to this exact example, right? Or to this specific example. So it tells me right there that my H naught is mu equals 100, bless you. And my HA is mu is greater than 100. Is everybody following there? 100 is what we would call mu naught in general terms. And this information has just been given to me in that first line, right? So it says, test the null hypothesis that mu is 100 against the alternative that mu is greater than 100 using alpha equals 0.05. So what's our test statistic going to be for this? The mu, so we're testing the mean, and we're going to, and the n is greater than or equal to 30, so what are we using? The z-test. Okay? So now we're going to find our rejection region for alpha equal to 0.05. So this is a one-tailed test, and it's just to the right? Here's our graph. So I know this area over here is 0.05, but I need to find this z-value that corresponds to that. Right? And that'll be how I set this rejection region. So I'm looking for the z that corresponds to 0.45 in the chart. Does that make sense there, what's going on? How I'm finding this value? So since my rejection region, alpha is 0.05, and it's a one-tailed test, that means this area is 0.05, so I need to find the z-value that has 5% of the area under the curve to the right of it. So what I do is go to the chart and find where 0.45 is. And we've done this a bunch of times. It's just a 90% confidence interval, right? This is a number we're going to see, or we've seen a bunch of. What is it? And in the chart, I believe it's in between. 773. So we're going to go to 0.45 exactly, which is going to be 1.645, right? Because it falls in between. It falls in between 1.64 and 1.65. So it's z. Z must be greater than 1.645. And that's a value we've seen a lot of. Right? That's just our 90% confidence interval value. If we go back and look at, which I'm not sure if I can go back to the correct part. I think it just allows me to go to 6.3. Or maybe I have the book open. Oh, I do have it open. So let me go to in here. So it's on page 358. Right here, remember looking at this yesterday? This is definitely an upper-tailed test, so I need to look in this column. Does everybody agree with that? Right? It's an upper-tailed. And alpha is 0.05, so there's my rejection region. Z must be greater than 1.645. which is what I have written down. Is everybody good with that? Following along? See where this stuff's coming from? Right? And the reason I know it's an upper tail is because this is not a not equal to, right? If this would have said not equal to 100, I would have to test below and above. Right, it'd be a two-tail, exactly. But it's not. It's only a one-tail. Assumptions, I can go ahead and assume the central limit theorem because n is greater than 100, or n is greater than 30. So now let's go in and calculate our z statistic. Let me pull back up the homework assignment. So here it is. So our z statistic, so this is step 6. I'll go ahead and do it on this board right here. So number 6, our z statistic is always equal to x bar minus mu naught, whatever the mean is in the null hypothesis, divided by s over square root of n. Right? It's our formula for z. So I'm just going to plug in the values that are given to me. So that implies that z equals, what's our sample mean? 111, right? With a sample mean of 111. I know that's kind of hard to read. So it's 111 minus 100 divided by, what's our sample standard deviation? That's really big, especially when compared to the mean. Right? So that kind of gives us a little bit of insight of what's going to happen here. But let's go ahead and keep going. So it's 63 divided by the square root of what? 100. The fact that n and mu were 100 is just coincidence. That's just this one problem. Right? Maybe this is July days in Portales where the average temperature is 100 degrees. Right? And they do 100 days. So let's go ahead and punch that into the calculator. And remember to go ahead and just put the numerator and denominator in parentheses so there's no issues with order of operations. So then turn it on. Autofocus. So it's going to be, that's not very bright, huh? So I'm going to do open parenthesis, 111 minus 100. So that's my x bar minus mu, or mu naught, the population, the value that we're testing, basically. Divided by, open parenthesis, 63 minus second square root of 100. And then you press to the right and close the parenthesis. It is divided by, excuse me. That would be way off. There we go. And the only thing I would say is make sure after you hit the square root of 100, it wants to put that parenthesis under the radical. So make sure you push to the right. Put the parenthesis on the outside. So then hit enter. So that's our z value. Z is 1.75. Let's round it to 2 decimal places. Is approximately 1.75. So what's our conclusion? Can I make another z? Does z lie in our rejection region? Is this number greater than this number? Yes. So therefore, we reject, because this is our region that we get rejection. Okay? So since this number lies in this shaded area over here, right, because I found that my rejection region starts at 1.645, 1.75 is over here. It's in the shaded area. It is in the rejection region. So therefore, our conclusion is we reject H naught. So since 1.75 is greater than 1.645, which is just our rejection region, we reject H naught. And accept HA. Now what our task is today in section 8.4 is to find what's called the p-value, or the level of significance. All that is the area under the curve to the right of whatever our z statistic is. So the same way we found the area to the right. So all I do is go read the Z chart. Find 1.75, do 0.5 minus that value, and that's my P value. My level of significance. Because what that means is the area to the right of where it gets rejected is significant. We'll see that as I get into the book. But so there's my conclusion. We reject H naught. So let me go back to the homework assignment. Notice how it doesn't say H naught is accepted, H naught is rejected, right? It's either not rejected or it's rejected. And which one was it? It was rejected. But I have a 5% chance of rejecting H naught when in fact it's true, which is type 1 error, right? That's alpha. So that's really, depending on the situation, a 5% chance of an error is too much, right? Maybe if we're talking about how much your cake rises in the oven, that's not that big a deal. But if we're talking about airline mechanics, right, or something like that, then it's a big deal. So it really depends on the situation. Interpret the result of the test. There is sufficient evidence to indicate the true population mean is smaller than 100. The true population mean is not equal to 100, or the true population mean is greater than 100. Greater than, because that's what our null hypothesis was, right? Or our alternative, excuse me. We rejected H naught, and we accepted HA, which says the mean is greater than 100. So that's our interpretation. There is sufficient evidence to indicate the true population mean is greater than 100. Hit C and hit Enter. Test the null hypothesis that mu is 100 against the alternative hypothesis that mu is not equal to 100. So what's this do now to our... Makes it a two-tailed test. So let's go back and start back over. So I'm going to go ahead and erase this. So now my HA changes to not equal to 100. Is my test statistic going to change?
No.
No, it's still going to be the Z-test. But now my rejection region does change, right? Because it's going to be the absolute value of something, because it's a two-tailed test. And I want to start writing it this way so you get used to looking at it, right? So the absolute value of Z, so what it's going to be is our two-tailed test now is here and here. So here's 0. So it's that area and this area, where this area, the left tail is 0.025 and the right tail is 0.025. How do I know that?
0.05.
Because in my alpha is 0.05. So in each of the tails is going to be half of it. So now I need to find Z that corresponds to 2.5% of the area being to the right of it. So what's this area here from 0 to Z?
0.5.
Well, the whole thing is 0.5, so this piece is 0.475, right? Is this piece right here?
Which would be 0.5 minus 0.025, right?
Well, no, we're looking for Z, so we need to look for this value in the chart. Remember? Yeah. Right, exactly, which is 0.5 minus 0.025. Yes. Good job. Okay, so now let's go find the Z that corresponds to an area of 0.475. So I still have my textbook open. And of course, we can get in here and answer this question from right where I was. So let's double check it off the chart. So we're looking for 0.475. Looks like right there. 1.96. You guys agree with that? So if we go back to where I was, 358, look what it says for a two-tailed test with alpha equal to 0.5. 1.96. So it's the same value. That's where it comes from. So Z, the absolute value of Z must be greater than 1.96. That is equivalent to saying Z is less than negative 1.96 or Z is greater than 1.96. Because it's absolute value. So even if Z was negative 2, if it happened to lie down here, the absolute value of negative 2 is still greater than 1.96. Because the absolute value of negative 2 is what? positive 2, which is still greater than 1.96. So that's why we write it in absolute value terms. So our assumptions are the same. It's approximately normal because n is greater than 30. But is the z statistic, is our test statistic going to change for this next question? Let's look at it again. Nope. Because it doesn't tell us a different mean, a different sample mean or a different standard deviation. So our test statistic stays the same, right? It's still 1 point, it's still right here. That's still the value of our test statistic. But what's going to be our conclusion? Since 1.75 is not greater than, or I could put less than, which is the same thing, but I want to say that it's not in the rejection region. So I'm going to write the greater than sign with a not. Does everybody agree that 1.75 is not greater than 1.96? So what does that mean?
It's not in the rejection region.
It's not in the rejection region, so we don't reject H naught. Right, exactly. We fail to reject H naught. Or H naught is not reject, same thing. Okay? This is how I learned to say it when I was in stats, so I guess that's kind of how I like to talk about it, because that's how I learned it. From a statistician that worked at Berkeley. And yeah, I don't know if you guys ever met Mir Mortazavi. He used to be a statistician here at Eastern. He retired about 4 or 5 years ago. So H naught is not rejected. Oh. So what's our conclusion? Smaller, not equal, or greater? And notice how it has insufficient, insufficient, and then it throws sufficient in there. So you really got to read these pretty carefully. Which one is it?
Not equal.
The one that's not equal. This is the only one that talks about not equal, so that's kind of a giveaway. You know, if I would have wrote this question, I probably would have had both of these be not equal. One say insufficient, one say sufficient. So then you have to pick the right. But it's definitely part B. There is insufficient evidence to indicate that mu is not equal to 100. There we go. Okay? So once you get your null hypothesis set up, right, your null and your alternative, once you get step 1 and step 2, right, because this is really the intuitive part, once you get that set up, everything follows along pretty seamlessly from there. All right. Compare the results of the two tests conducted. Explain why the results differ. The results differ because HA in part A is more specific than in B, or the results differ because the alternative hypothesis in part B is more specific than the one in A. And it's definitely not C, right? Because they do differ. Which one is it? What do you guys think?
It's more specific if it's not. No?
It's more specific if it covers both tails. If it's just a one-tailed test, it's not as specific. Does that make sense? Because it's two-tailed, so it means less than or greater than. And then if you click this show completed problem, it'll give you. In part A, so my interpretation was wrong. I was backwards. Part A specifies only one area, whereas part B specifies two separate areas. So I was backwards in my interpretation, excuse me. I wouldn't probably ask you that question on a test. I mean, specific could be defined in a lot of different ways. So that's kind of a funny question, if you ask me. Part C is. What's important is that you can answer this question right here. Is H naught not rejected, or is H naught rejected? All right? Okay? And then so this shows the whole completed problem. Set up H naught and HA for testing whether the true mean disclosure of all adolescents exceeds 3. Which one's that going to be? You don't even really need to read the top part to answer that question.
So it needs to be greater than?
Has to be greater than.
C.
So C is the answer. Yep. There you go. And this is a very significant test. See how alpha is really small? It's 0.01. But this is definitely an upper tailed test, right? A one tail, upper tail. Okay. All right, so let's look at some of the new stuff. Let me jump back to the... Oh, what's up with that pop-up blocker stuff? So 8.4. 367. Yeah, you'll notice that this chart comes in very handy when we're doing this stuff.
Will that be in the house?
I haven't completely decided yet if it is or not. I'll let you guys know Monday. As of right now, no. Right? So that way you study. Because I found whenever you say, oh, you'll have it on the formula sheet, then students don't spend nearly as much time studying it. Which, I mean, is human nature. You probably noticed that in most of your classes, right? The teachers always say study everything, and then at the test time they give you the extra information. That's normal practice. All right, so 367. Now this p-test stuff, it seems kind of weird at first, but it's really pretty simple. All right? So let's check it out. And you guys, after we read through it, you'll probably say, that's it, huh? Which is kind of how this hypothesis testing, at first it seems really difficult, like there's a lot of stuff going on. And after you get into practice on it, it's really not too bad. Right? So according to the statistical test procedure described in 8.2, which was finding the rejection region, was section 8.2, correspondingly, the value of alpha are selected prior to conducting the test, right? Alpha has to be given to you at the beginning. It's something that the researcher just has. And they say, here's alpha. Test it with such and such level of significance. And the conclusions are stated in terms of rejecting or not rejecting. A second method of presenting the results of a statistical test reports the extent to which the test statistic disagrees with the null hypothesis. Which kind of sounds weird at first, but we'll see exactly what that means. And leaves to the reader the task of deciding whether to reject the null hypothesis. This measure of disagreement is called the observed significance level, but what I'm going to call it is the p-value, right, for the test. So let's write this definition down. The p-value for a specific statistical test is the probability of observing a value of the test statistic that is at least as contradictory to the null hypothesis and supportive of the alternative hypothesis as the one computed from the sample data. Now that definition is really not that clear. But this next example really explains what it's talking about. Basically what it wants is the area to the right of your calculated statistic. Or to the left, depending on which tail it's in. Or both if it's a two-tail. So really what the p-value does is goes to part 6 where we calculate the test statistic. And it's just the area to the right of it. That's it. So what's the probability that we observe a test statistic that is greater than the one we found in step 6? So recall, once again, going back to our pipe burst example. Remember, mu was 2,400. We tested it against mu being greater than. So we wanted to know if the strength of the pipe was actually greater than 2,400 pounds per linear foot. So this is definitely a one-tailed test, right? You guys agree with that? Upper tail. Now, as they went through it, they told us that their test statistic was 2.12. Which, for this problem, I think we had alpha was 0.05, so we did reject H naught. But all the p-value is is the probability that z is greater than that value. So all it is the area under the curve to the right of the test statistic. So write that down. The p-value is the area under the curve that lies beyond. So don't say to the right, because it could be a two-tail. The p-value is the area under the curve that lies beyond the test statistic. So, the p-value is the area under the curve that lies beyond, so I say beyond because to the outside, the test statistic. So for this, we really don't even have to go through all the hypothesis testing. We just have to skip to step 6 and figure out the area outside of it. That's all we have to do. Yeah?
Past the rejection region?
Yeah, it'll be past the rejection region, right? So on this, on the second one we did today, it didn't reject, so we wouldn't find the p-value of that. But on the first example, where we did reject it, right, our rejection region was 1.645. The p-value would be the area to the right of 1.75. So there's a little slit of area between 1.645 and 1.75 that wouldn't be included in the p-value. Does that kind of make sense there? And we'll see it in a few more examples. So this is going back to the first example we did today of the one-tailed test, where we found that, so here was 0. So our rejection region was to the right of 1.645, right? So this was alpha. And what we found was our z statistic was 1.75. So the p-value would be the area under the curve to the right of 1.75. Do you see that? So we wouldn't count this little sliver of area in the p-value. So the whole thing is alpha, but only this piece right here is the p-value. Those are some pretty ugly brackets. That makes sense? You guys see what's going on there? So the p-value will almost always be, the p-value will always be less than or equal to alpha. Does that make sense? It could be equal to, if our z statistic we came up with was exactly the same as 1.645, then we basically would have to do a little bit more testing. Yeah, you'll never get a z statistic that's going to lie directly on the line in this class. I mean, you could in the real world, but not in this textbook. So this is something that will always be true. That's a good way to check that you got the right answer. The p-value will always be less because it's the area to the right. Now, this is just when we reject H naught. If we don't reject H naught, then it doesn't make any sense to do this. Right? Everybody kind of see from my little drawing here what's going on? Okay? So the p-value here would be 0.5 minus whatever z is at 1.75. Okay? But we'll go in and look at a few more examples. Okay. So here's basically a picture of what we just drew, or what I did, but this is for the pipe bursting problem. I think for the pipe bursting problem, it was 1.96 was my alpha, right, or was my z, was where my rejection region was. So the p-value is just the thing to the right of whatever the z statistic is. So the p-value is definitely included in alpha. The p-value is part of alpha. They are not mutually exclusive, right? They have something in common. And I think this chart, this picture really does a little bit better job. And this will always be true. The p-value will always be less than or equal to our level of significance. As long as H naught is rejected. Okay?
So you only find the p-value if H naught is rejected.
Right, exactly. And that's because of the definition. It says, of observing the test statistic that is at least as contradictory to the null hypothesis as the actual one computed from the sample data. Now that's a good question about it not being. Now in all these examples from the book, it's always when H naught gets rejected. So there could be instances where the p-value is greater than alpha, but we don't see them in this book. All right, we only deal with where H naught gets rejected. That's something that we'd probably cover in Stat 313. Right? So let's look at another example so we can really wrap our mind around this. If you are inclined to select alpha equals 0.05 for this test, then you would reject the null hypothesis because the p-value for the test is 0.0170 is less than 0.05. Oh, okay, so there it is. There's the answer. I jumped the gun on that statement. So what's nice about this is we don't have to worry about finding the z that corresponds to 0.05. We can just simply find the p-value and compare it to alpha. So let me rewrite this. The p-value will be less than or equal to alpha. Then we reject H naught. And if the p-value is greater than alpha, then we do not reject H naught. So excuse me on that. In contrast, if you choose alpha equals 0.01 and we get a p-value of 0.0170, everybody agrees that 0.0170 is greater than 0.01, right? So then we would fail to reject the null hypothesis. Thus, the use of the observed significance level is identical to the test procedure described in the preceding sections, except that the choice of alpha is left to you. The steps for calculating the p-value corresponding to a test statistic for population mean are given in the following box. So that's it. Which this is a lot easier, right? Than going through all those steps. You just simply find the p-value and compare it to alpha. That's it. So steps for calculating the p-value. Step 1, determine the value of the test statistic z corresponding to the result of the sampling experiment. That's step 6, right? If the test is one-tailed, the p-value is equal to the tail area beyond z in the same direction as the alternative hypothesis. Thus, if the alternative hypothesis is of the form greater than, the p-value is the area to the right of. Consequently, if it's less than, then the p-value is area to the left of the z-statistic, which is pretty self-explanatory. If it's two-tailed, the p-value is equal to twice the tail area beyond the observed z-value. So it's the same thing. So here, if alpha p-value, we would reject. If alpha was smaller than the p-value, we would fail to reject. Right? So my first statement up here was exactly true, but it works in both directions. Right? If the p-value is less than alpha, we reject H naught. If the p-value is greater than alpha, then we fail to reject H naught. Okay? So all we're doing here is we're going to step 6 and finding the area under the curve, right, to the right of what we find in step 6. The p-value is the area under the curve that lies beyond the test statistic. Here's my test statistic, the area that lies beyond it. All right, so here we would multiply both of those together, or add them together. So notice how it's p over 2 and p over 2. So it's really a straightforward way to do testing.
Is it not the same as the alpha? The pictures for the alpha? When they show
No, it is. Yeah, it's exactly the same. Yeah. The difference is we were comparing our z, the z value. This section is comparing the areas. That's the only difference. Because before we compared just the values along the horizontal axis. So we weren't comparing the area under the curve. We were actually comparing what the z statistics are. Now we can go ahead and just compare the areas. So it's really the same thing. It's just what are you looking at? Are you looking at the area under the curve, or are you looking at the z value that corresponds to that area under the curve? All right? To me, this one's easier. P-value. So let's look at an example. Okay. So it says, computing p-value, test on mean drug response time. So this is going back to our rats again. Our juiced up rats. Find the observed significance level, which is the p-value, for the test of the mean response time for drug-injected rats in examples 8.3 and 8.4. So we're testing H naught against HA. I'll leave my H naught and HA up. So here our H naught is mu is 1.2 against the alternative hypothesis that mu is not equal to 1.2. So is this a one-tail or two-tail? Definitely a two-tail test. Okay. So our alpha for this was, I don't want to flip to the next page and give away all the answers. Let me go to the page that has the alpha so we can write the correct alpha down. Alpha is 0.01. So let alpha equal 0.01. And our z statistic from this, our z stat, was equal to negative 3.0. So this is all stuff that's been given to us previously, all right? Our alpha was 0.01, so 3 said the z stat. This was basically number 4, right? Setting up our rejection region. This was step 6, was finding the z statistic. So let's go ahead and draw a picture. Okay. So here's 0. And this is a 99% confidence interval on a two-tailed test. So what was z, remember, on the alpha 0.01 for a two-tail? You guys remember? 2.575. Negative 2.575. So this area was alpha over 2, right? Was that entire area? And this area was alpha over 2. Now, obviously, negative 3 lies to the left of this value, so we would go ahead and reject it. But let's find the p-value for this. So I want to find the probability that the absolute value of z is greater than 3. Which is equal to 2 times the probability that z is greater than 3. So this includes both tails, right? Because I have the absolute value. So the area in one of the tails is going to be equal to the amount of area in the other tail. So I could just find it for 3 and multiply it by 2. Does that make sense? Which is what's going on the next page. So let me flip to the next page. Here we go. The observed value of the test statistic in example 8.4 was z equals negative 3, and any value of z less than negative 3 or greater than positive 3, because it's a two-tailed test, would be even more contradictory to h naught. Right? If it lied beyond 3, it'd be even more contradictory. Therefore, the observed significance level for the test, the p-value is equal to the probability that z is less than negative 3 plus the probability that z is greater than negative 3, which is equal to the probability that the absolute value of z is greater than 3. And since it's two-tailed, right, isn't the area contained less than negative 3 going to be equal to the area contained greater than positive 3? So you could just go ahead and do 2 times, which I would do positive 3 myself, but because that's what's in the chart is the positive values, right, not the negatives. So what is less than negative 3, which I'm doing greater than positive 3, which is the same thing. So what's the area under the curve to the right of 3? Let's go look at our book. So here's 3.0 right there, boom. So that's the area to the left of 3. So how much area is to the right of it? What do I do? 0.5 minus that, right? Okay. So this equals 2 times 0.0013, right? Does that make sense? What is 2 times 0.0013? 0.0026. Is my p-value less than alpha? Yes, right? Does everybody agree that 0.0026 is smaller than 0.01? So, since my p-value is less than alpha, we reject h naught. It's just a different way to interpret the results. That's all the p-value is. Question? So what we can't do is we can't mix these numbers with the areas. And I did see that some on the test. So we can't, remember, z values do not have anything necessarily to do with the area under the curve. All this area added together is only equal to 1. Right? To the right of 0 is just equal to 0.5. So since this happens, we reject h naught. Yeah, sure. So actually, there's alpha over 2 and alpha over 2. Here's negative 3 and positive 3. So this is p over 2, and this is p over 2. But alpha over 2 is all of the area.
And we just have to multiply by 2
Because it's two-tailed.
And the 0.0013 you got,
From right here.
and that's 5.
Because I want to know the area to the right. Right? Because I want to know this area, the tailed area. So with z is 3, the area between 0 and 3 is 0.4987, so the area to the right is 0.0013. Okay, so here's basically the operations that I just did. Notice we came up with the exact same value, 0.0026. This p-value can also be obtained with statistical software, which we don't really mess with. Or what I could have done, Oscar, is I could have found this area and then added it to that area rather than multiply by 2. But the reason I'm doing both is because it's a two-tailed test. If it was one-tailed, then I wouldn't worry about this times 2. Right? I wouldn't worry about the times 2. Then the p-value would be 0.0013. Okay? So let's look at this box down at the bottom of the page. Reporting test results as p-values. How to decide whether to reject H0. Choose the maximum value of alpha that you are willing to tolerate. So that depends on the situation. For all of your homework assignments, you'll be given a value of alpha. All right, you won't just have to choose one. If the observed significance level, if the p-value of the test is less than the chosen value of alpha, reject the null hypothesis. So that's basically just restating what I have written right here. Right? If the p-value is less than alpha, then reject H0. Otherwise, fail to reject H0. Now, if your p-value and your alpha are exactly equal, then you kind of have to look a little deeper into the test. But you guys won't see any on your homework where they're equal. Right? If they are equal, then we would still reject. Okay? So this is kind of restating our rejection region. So see how they're kind of, the rejection region and the alpha are synonymous with each other, right? And the p-value is just the area of the rejection region to the right of your z statistic. All right. So let's look at another example to drive this point home. Okay. Length of hospital stay. Length of stay in days for 100 randomly selected hospital patients, first presented in Table 7.1, are reproduced in Table 8.4. Suppose we want to test the hypothesis of the mean equal to 5 or less than 5. So is this a one-tail or a two-tail?
One
Upper or lower?
lower.
Lower. Good job. Okay, good. So let's go. So our mu is 5, and then we're testing whether mu is less than 5. Alpha is 0.05. So let's draw a picture representing that. That's 0. I know that's not the prettiest picture I've ever done. There we go. So here is alpha equals 0.05. That's our rejection region. Everybody following along? Make sense?
Or the p is 0.05.
Our p isn't 0.05. Our alpha is 0.05. Yeah, we haven't found p yet. Our p value.
And why did we use 0.05?
Oh, because it was given to us right here.
Oh, okay.
Yeah. And it gives us a standard deviation. I don't want to go through and find the mean of all those 100 points. I'll just give it to you. Okay? So X bar for our 100. So X bar for all of the average of all those lengths of stay is 4.53. My sigma was given to me, and it is 3.68. And what's N? 100. So let's find our Z statistic. So Z equals X bar minus mu over sigma divided by the square root of N. So that's equal to 4.53 minus 5 divided by 3.68 divided by the square root of 100. Now, I could just look at the Z that corresponds to this and do it like we've done it in the past, but I'm going to do it using the p-value. Right? So what is my Z that corresponds to this? My X bar was given as 4.53. So what does this come out to when you punch it in your calculator? .68 divided by. And round it to 2 decimal places. So what do we get? Negative 1.28, right? Let me look at what you put in your calculator. Oh yeah, you don't want to round that. 0.453 is that number. 4.53. And you didn't round, which is fine. That's what was wrong. 4.53 divided by, or minus 5. Okay. And do your other one. See, you're off. Because what it does is it does your order of operations wrong, differently. So that's why you're getting a weird number here. You're off by 100. It should be 1.28. It's because of the way it's interpreting the order of operations here. Do them separate. Yeah, use the parentheses. Put that denominator in parentheses. But we get negative 1.28. So what's the probability? So my p-value will be, let me do it on this board. So my p-value equals the probability that Z is less than negative 1.28. So how do I find that? My p-value is going to be equal to 0.5 minus the probability that Z is between 0 and 1.28, negative 1.28, right? So what is the 1.28 from the table? Let's go back here to 773. What do we get for 1.28? That's not quite up there. So 1.2, go across. 1.28 is 0.3997. So 0.5 minus 0.3997, which equals what? 0.1003, I believe. So, what's our relationship from the p-value and alpha? Which one's bigger? Alpha was given to us as 0.05. So what's bigger, 0.05 or 0.1003? So that means the p-value is greater than alpha. Which, what's our conclusion? If the p-value is greater than alpha, we fail to reject. Which makes sense because what's the z-value that corresponds to 0.45? It's right here. 1.645. So this value is 1.645. Our z, negative 1.645. Our z statistic was negative 1.28, so it definitely doesn't fall in the rejection region. So the p-value is just another way to interpret our rejection region, right? It's a different way to do the same thing. One is comparing the areas. So we learned comparing the z-values, right? That was how we did it first. What the p-value does is compares the areas. So look, here's my p-value. Right, it's the area that lies beyond the test statistic. Notice the area on my p-value is greater than my area in alpha, so therefore I would fail to reject. Does that make a little more sense after seeing it like that? So one, we learned comparing these two values. All the p-value does is compares the areas. But it's the same thing. Right? We're looking at the exact same stuff. Okay? What's that? What's on? Oh, just my calculating my p-value. So the p-value is 0.5 minus the area between negative 1.28 and 0, which is this number. So therefore my area that lies beyond negative 1.28 is 0.1003. Okay? Which to me, I like the p-value a little bit better because we find the z statistic and then read the area from the chart. Because this chart was meant to be given a z and then find the area. It wasn't really meant to try and locate the area and then work backwards to find z. Does that make sense? It's easier to be given a z value and then find the area, as opposed to working backwards, where you have to comb through all these numbers to find the one you're looking for. Alrighty. Pages out. And that's it. That's 8-4. Uh-oh. My session has expired. See, and there's the new sign-in screen. Let's go look at a couple homework assignments, and then I'll begin 8-4. Because really, you guys have all the tools to do, or begin 8-5. Because you guys have all the tools for 8-5. It's just now, instead of using the z statistic, we'll use the t statistic. So that's the only difference for 8-5. Well, let's look at a couple examples in 8-4. Preview. Whoa. If a hypothesis test were conducted using alpha equals 0.01, for which of the following p-values would the null hypothesis be rejected, A or B? B, because it's less than alpha, right? This is what you need to really have written down, are these two statements right here when you're doing this homework. Make sure you have these two statements written down. If the p-value is less than alpha, and I'll go ahead and just kick that or equal to out, we reject H naught. If the p-value is greater than alpha, then we fail to reject. So in part A, the p-value is greater than alpha. So we do part B. We do not reject the null hypothesis since the p-value, and instead of putting greater than, it puts not less than. All right, which is slashing out the less than sign. Which I would say greater than, but it's not less than. So the answer there would be B. Does everybody see why? It's because of these two statements I have written on the board over here. Part B, would we reject? If the p-value is 0.007? Yes, right? We would reject. Because the p-value is less than alpha. Because alpha was given to us as 0.01. So therefore, we would reject the null hypothesis since the p-value is less than the value of alpha. Okay? And for these other problems, it gives you H naught and HA. So really all we need to do there is know that it's a two-tailed test. You don't really have to go through all the steps. It gives us X bar and S and N. So we can find our Z statistic and then find the area that lies outside of it, right? And compare it to, so first it says find the p-value. So we haven't been given an alpha. This just says find the p-value. Find the area that lies beyond our test statistic. And here it'll be two-tailed, right? Because it's not equal to. So let's go ahead and just do this one. And then we'll get into 8.5. Okay. In a test of hypothesis, H naught equals 10 versus HA is not equal to 10. A sample of N equals 50 observations is conducted with an X bar and an S. So let's find the Z statistic. We're able to use Z because N is greater than or equal to 30. So Z is equal to X bar minus mu over S divided by the square root of N, right? That's our formula for Z. So let's plug in our specific values. What's X bar? 10.6 minus mu, which is 10, divided by 2.5, divided by the square root of 50. Make sure you put the numerator and denominator in parentheses so there's no order of operations errors. So we get Z equals what? So it's 0.6 divided by 2.5 divided by square root of 50. Round to two decimal places. What do you guys get? 1.7. But this is a two-tailed test, right? So our p-value, right, you've got to multiply it by 2. So our p-value is going to be equal to 2 times the probability, well, let me put it like this, 2 times the probability that Z is greater than 1.7. And then the probability that Z is greater than 1.7 is going to be 0.5 minus, so 2 times 0.5 minus what it is between 0 and 1.7. So we get that from the textbook. I don't have, oh, here, I'll just look at it in here. So what is it at 1.7?
0.4554.
Okay. 0.4554. 0.4554. So that equals 2 times point what? 0.0556? No. 446. That's right. Right, that's 0.5 minus 0.4554.
Right.
And then 2 times it is going to be 0.0892. Everybody agree with that? All right, so that's our p-value. 0.0892. And there it is. So basically what that means is we have about an 8.9% or a 9% chance of rejection. Or of it being greater than that. Not rejection, because we haven't been given an alpha yet. And we don't even get an alpha on this particular question. Okay? That's it. All right. So let's go begin 8.4. 8.5, excuse me. So Multimedia Library, Chapter 8. Everything is exactly the same, except for now we're using the t statistic instead of the z. Everything else is the same, though. All right? Our steps are the same. The way we find our rejection region is the same. We just use our t chart instead of our z chart. So here we have to worry about, what do we have to worry about in the critical values of t? What was that other thing? Degrees of freedom, which is n minus 1, right? The sample size minus 1. So let's look at this example. We'll go through this example and then probably call it a day. All right? Most water treatment facilities monitor the quality of their drinking water on an hourly basis. Really, you probably want it every minute, right? If we're talking about drinking water here. Now, this is something we would want our level of significance to be very small, right? Our alpha to be small, because we want people getting sick. So you wouldn't want a 90% confidence interval. You'd want 99, right? You'd want alpha to be like 0.01. A pH below 7 is acidic, 1 below 7 is alkaline, and a pH of 7 is neutral. Regular water should have 7, right? Well, most of the water pulled out of the ground around here has more alkaline in it because of what is in the ground, right? It's a little more basic, which is what? Alkaline, another word for it is a base, right? One water treatment plant has a target pH of 8.5. Most try to maintain a slightly alkaline level. The mean and standard deviation of 1 hour's test results based on 17 water samples. So this tells us what our sample size is. Is that big enough to use the z statistic? No, it's got to be greater than or equal to 30. So right away we know we're going to have to use the t statistic. Does this sample provide sufficient evidence that the mean pH level in the water differs from 8.5? And this is a good one that we just care about differs, because we don't want it to be more than 8.5, and we don't want it to be less than 8.5. We want it to be exactly 8.5. We establish the target pH as the null hypothesized value, right? That's our status quo. And then utilize a two-tailed alternative hypothesis that the true mean differs. Everybody realizes that's a two-tailed test, right? Okay. So there's two things that have to happen when we use the t-test. One, the samples have to be taken at random. And number two, the population from which the samples came from has to be approximately normal. Because we can't use the central limit theorem here because we don't have enough observations. The normality of the sampling distribution of X bar does not follow from the central limit theorem when the sample size is small. We must assume that the distribution of measurements from which the sample was selected, so all the measurements, the population of measurements, is approximately normal in order to approximate the normality of X bar. That was just a definition from 7.3. The population standard deviation is unknown, but we can go ahead and use sigma will provide, or S will provide a good approximation for sigma. So recall our T, it's exactly the same as Z, right? It's X bar minus mu divided by S over square root of N. Really, the only difference with this is you read it from a different chart. Other than that, everything else is exactly the same. All right? Remember, the T values were a little more spread out than the Z values. So a 95% confidence interval with T was like 2.5 or something, where for Z it was 1.96. Remember, it was just a little bit farther out. So what they do is they go ahead and let alpha equal 0.05. So here's our rejection region. So this isn't finding the p-value. This is just doing the t values. So it found the rejection region because alpha was said to be 0.05. The rejection region is going to be greater than 2.12 or less than negative 2.12 because it's a two-tailed test. And that value comes from the chart. So let's go practice reading that chart again, 775. So alpha is 0.05. Which, since it's two-tailed, we need to look for t of 0.025. So we got to look in this column, right? Because the area of one of the tails is 0.025. Because it's a two-tailed test, right? And what's my degrees of freedom going to be here? Because 17 minus 1, right? So 16 and 0.025, right here, 2.12.
What page is that?
775. It's the page after the Z chart. 775. So now we go in and calculate our t statistic in exactly the same fashion as we do our z statistic. That's 374. So X bar had, so all these values had to be given to us. .42, 0.16, all this stuff had to be given to us, which you will have it given to you in your example. Oh, it was given to us at the beginning of this. Look, here's my X bar. There's X bar and S. 8.42 and 0.16. So that's what I plug in for X bar. That's what I plug in for S. N is square root of, N is 17, so it's square root of 17. 8.5, this is the value that we're testing, right? That's from our null hypothesis, right? Which is right here. So after I plug all this in and punch it through my calculator, I come up with negative 2.05. Does that lie in the rejection region? Yes or no? What do you guys think? Do we reject H naught?
It is not less than.
It is not less than, so therefore we fail To reject. Right, it says right here, since the calculated value of t does not fall in the rejection region. Now this is not the p-value, right? The p-value is the area under the curve to the left of negative 2.05, and to the right since it's a two-tailed test. But this isn't asking for the p-value. We cannot reject H naught at a alpha equals 0.05 level of significance. Thus, the water treatment plant should not conclude that the mean pH differs from 8.5 target on the basis of the sample evidence. Now, if it was me, I would probably make my alpha a little bit smaller. I'd like to be a little more sure about this. So I'd want to make it really 0.01. All right?
So if we fail to reject, then we're getting the numbers that they're asking for, which is...
Right. So the mean pH is around 8.5. There's not significant evidence to suggest that it differs from 8.5. So basically, the water treatment plant is in control, right? Because we did not reject H naught. It is interesting to note that the calculated t-value, negative 2.05, is less than the 0.05 level z-value, 1.96. So if this would have been a big sample, we would have rejected. Right? Because this would have been the z. My rejection region for the z would have been negative 1.96. Then it would have been rejected, right? Then it would fall in the rejection region. The implication is that if we had incorrectly used a z statistic for this test, we would have rejected the null hypothesis at the 0.05 level and concluded that it's out of control, that the mean differs from 8.5. The important point is that the statistical procedure to be used must always be closely scrutinized and all the assumptions understood. Here our assumptions were we had to use the t-test because our sample size wasn't big enough. Many statistical lies are the result of misapplications of otherwise valid procedures. Now that happens a lot in today's world, all right? You know, you'll get a statistic and it's skewed, right? Like the unemployment rate. That does not take into account that the fact that our workforce participation is the lowest it's been since the early 70s. Even though the unemployment rate looks small, in actuality it's not because of the way that it was forecast. And when you consider that our population's increased, I mean, if you consider all people that are of working age, I mean, the unemployment rate is something like 12 or 13%, right? So that's what this is saying. Many statistical lies are the result of misapplications of otherwise valid procedures. That's an example of it. The technique for conducting a small sample, and you'll notice this is exactly like the box for the t-test, or for the z-test. The only difference is we're using t instead of z. So see how 8.3 is really the cornerstone for this chapter? Everything else kind of piggybacks off of it. Okay? So this is step 1, step 2, step 3, step 4. Right there. Step 5, the assumptions would have been that we have to use the t-test because our assumptions here would be the population would have to be approximately normal. We are assuming. That's why we're using the t-test. All right? And then step 6 would be what we did right here, calculating the t statistic. And then step 7 would be our conclusion right here. We failed to reject H naught. Okay? And then conditions required. This is the exact same conditions we saw in section 7.3. First of all, the most important aspect of sampling is that they had to be selected at random. And number 2, the population for which the sample is selected has a distribution that is approximately normal. We have to assume that because we can't invoke the central limit theorem because our sample size isn't big enough. So we have to assume that the population is approximately normal. All right, guys? What I'm going to do, I'm going to cut you out a little bit early. We're about 10 minutes early, so about 14 minutes early, actually. But where we'll start class tomorrow, so tomorrow is really the last day of lecture for the entire class. All right? Because Monday we'll review, Tuesday we'll take our 7 and 8 test, Wednesday we'll review for the final, and then next Thursday we'll take the final. So I'll start class off with this example, kind of go through 8.5, and then we'll get into 8.6, which deals with testing P. So up to this point, all we've done is test mu. And we need to keep the P value and the population proportion separate. They are not the same thing, even though they both have the letter P. Right? So we'll do this one tomorrow as well. So this is hypothesis testing for P instead of mu. We're not going to do hypothesis testing for the variance. Right? And P is the proportion or the rate or the percentage. Right? So there we'll just make assumptions like this. P is 0.2 or P is not 0.2. And basically we follow the exact same procedure. Now these will all be for large sample tests. So we'll be able to use the z-scores for this. Right? We won't have to worry about the t's, the t-test. Okay? All right, so your homework for 8.4 and 8.5 is due tomorrow. But I want you guys to come with questions over it, and I'll kind of see why that went back. Getting used to this new menu. So go in and try these, and I'll answer questions over 8.4 and 8.5 tomorrow. All right? Possibly I might push 8.5 back to Monday, but I want you guys to get in and try it tonight. And then I'll decide if I'm going to push it back tomorrow. But as of this point, just assume it's going to stay due where it is. All right? So really, you guys have the ammunition to do every section up to 8.5. All right? We haven't covered 8.6 yet, but you could do 8.1, 8.2, 8.3, 8.4, and 8.5. Okay? All right, where's my sign-in sheet at? It's over here. Yeah, make sure you hit that before you leave. Thank you, guys, and we'll see you tomorrow. You're free to go. And I'll send both the videos out here in a little while. I forgot to send yesterday's.
Actually did a pretty good job with these workouts.
They finally got my damn shirts and stuff, and I come here from work. If I go home after work, there's no guarantee that I'll fall asleep before that. This way. I'm sure they got a report week of August 29th. Oh, that's nice. It's coming up pretty quick. Should be getting orders within like the next 3 weeks or so. So they got a TMO your stuff? Yeah. Okay. Yeah, 'cause
I've done dating moves before, man, just to get the money from it, but it's not worth it.
It's really not.